Okay, last time I think I have left at this problem, and we were talking about the static equilibrium of objects. And remember, for an object to be in static equilibrium, if the object is extended, we require all linear forces acting on the object must be equal to 0. Also, all torque on the object must be equal to 0. So we have two conditions. Apart from the point objects, for extended objects, we have to include the torque. Okay, the capability of rotation of the forces also we have to include in the equations. So let's continue with this problem of ladder. It's a very common problem. So we have a ladder. It is supported by a wall and the ground, as you see, and we have also a person on the ladder. So the problem is find the forces F1, F2, and F3 in order to keep this ladder in static equilibrium. Okay, so the first thing is if you have such a object, you have to denote all the forces on it, like free body diagram. In free body diagrams, we have to show all the forces acting on the object at every point. And when you look at this object, the ladder, evet sessiz arkadaşlar. Sessiz. We have the weight of the person at this point, okay? And you may take the ladder, which is very...
Kumandan var mı acaba projeksiyon?
Ya ben nereden bileyim kumandayı? Ben ders yapıyorum burada. Allah Allah, her gene kumanda soruyor. So what you see in the picture, all the forces, one downward, the weight of the lady, and be very careful about choosing the forces F1, F2, and F3 at the contact points. Okay. You have to include the horizontal force on the ladder where it touches the surface of the ground. And you have to include the friction, okay? Think about this. If you had no friction, would you keep this ladder without sliding? There is no possibility. You have to have a friction. So once you have a friction, then this frictional force is always parallel to the surfaces, right? And there is also one more force, which is the normal force. If any object is in touch with a surface, there must always be normal force to the surface. Okay? So you have to denote this force as normal to the surface, not like parallel to the this ladder like this. Let me show it to you clearly. You might have also choose this contact force like this, okay? In this direction. But I advise you to choose the forces in components, one parallel to the surface, the other is perpendicular to the surface. This is the best choice, okay? So you have two forces. One is parallel, F2, we denote, and the other one is F1, the contact force, the normal force between the ladder and the surface. So once you set all the forces on the contact points and also the weight of the lady, you are ready to satisfy the equilibrium condition. The equilibrium condition says the sum of all linear forces must be equal to 0, right? So the first condition is this one. Sessiz arkadaşlar. The first condition is this one, and the second condition I will come to later. The torque, all the torque must be equal to 0. So they are both vectors. Okay, so we have to add these vectorially. That means you have to add the forces in the horizontal direction separately and the forces in the vertical direction separately. So the first condition gives you F1 minus mg is equal to 0 because F1 and mg are the forces which are in the vertical direction and they are in opposite directions, and we keep the upward direction as positive. That's why we take F1 plus and mg minus. So this must be equal to, right away, you have F1 is equal to mg. You just found from the first condition that what the F1 force must be equal to. The second one is the horizontal forces, and we keep the right direction as the positive, so F2 is plus, but F3 is the force, the contact force of the wall on the ladder. Okay. You might ask at this point, there must be a horizontal force also, right? But in these type of ladder problems, we usually take the wall as frictionless. There is no friction, okay, on the wall, and this will be denoted in the question. Okay, so in here there is no question body, but anyway, we keep these type of problems. The wall is always taken almost most of the time as the frictionless. Yes.
Hocam tork aldığımızda F1 çarpı o ladder'ın tam uzunluğu eşittir mg çarpı.
I haven't come to the torque point yet. I will explain. Okay, torque. So F2 minus F3 is equal to 0. That means there is a contact horizontal force by the wall and the frictional force by the ground. So these must be equal to each other. F3 is equal to F3. So this is the second condition coming from the linear static equilibrium. The next is we have to also think about these forces, the capability of these forces rotating the ladder. Okay, and if it is in equilibrium, there is no rotation. That means all torques is equal to 0. So mg, a force that is able to rotate this ladder, right? If you release, if you somehow change the forces on this contact forces, other forces, then mg may rotate the ladder around a fixed point. Let's call this point, choose this fixed point as the point where the ladder is in contact with the ground. So we choose a point before you start satisfying this torque equation. You have to choose a rotational axis, a rotational point. Okay? Before you write down explicitly these torque equations, you can choose, you can take any point. But of course, this point must should be able to solve these equations easily. Okay, choose any point so that you can write the equations in most easy form. So usually one of the points that the forces are applied should be taken as the point of rotation. So we choose this point. That means the rotation coming from F1 and F2 for this point will be equal to 0 because the forces have no distance to the rotational point. If the forces has no distance to the rotation point, that torque is 0 by these forces, because torque is the distance, the perpendicular distance of the force to the rotational point or axis. So you eliminate the torque expressions from these two forces right away if you choose this contact point as the point of rotation. The only left is mg. Mg has a perpendicular distance to the contact point. Let's call this B, okay? And in fact, B is given in the problem. Well, you might not see well in here. I will write it B is equal to 0.7 meters, okay? That is this distance, okay? This distance, this is the perpendicular distance of the point of application of mg to the point of rotation, right? It's very clear, I think. If it's not clear, I can explain more. So, and think in which way this mg will rotate the ladder, in counterclockwise or clockwise. If you think it will rotate in the clockwise direction, but we take always the clockwise rotation as minus, so that's why we have to put a minus sign in here. So mg times b is the torque by the weight of the lady to the ladder at the point, at this contact point. And only we have one force left. It is F3, and F3 is in this direction, and the perpendicular distance to the point of application is this distance, the height, and this is 3.8 meters. Let me also write it. A is equal to 3.8 meters, and it is this distance, the perpendicular distance of the application point of F3 to the rotational axis. So F3 times A, and A is 3.8, whatever. So you can right away solve this equation, the last equation. We have only one torque equation, okay? And in terms of M, G, B, and A, these distances. So F3 must be equal to this quantity, mg times B divided by A. So these, from this, since F2 is equal to F3, F2 is also mg B divided by A, and F1 is mg, so you just put the given values in these expressions, you can get numerical values for F1, F2, and F3. Do you have any questions?
Hocam orada F3 bu tarafı çeviriyor ya. MG'nin de aynı doğrultudaki bileşeni almak gerekmez mi orada? Çok tartışıyorlar da.
Neyi alması gerekiyor diyorsun mg'nin?
MG oradan merdiven üzerindeki bileşeni var, bir de aşağı sağ çaprazı böyle bileşeni.
Şimdi burada şuna dikkat edeceksiniz arkadaşlar. Eğer ben mg için düşünelim. Torku hesaplıyoruz. Bu noktadan şuraya olan mesafe değil mi? R. Ama mesele şu ki burada eğer mg çarpı bu mesafeyi almaya kalkarsan şu açıyı hesaba katman lazım. Tamam mı? Şu açı sinüs teta çarpı mg çarpı bu mesafe. Ya da mg'yi direkt aşağı indiriyorsun doğrultusunu. Bu doğrultu boyunca dönme noktasına olan dik uzaklığı alıyorsun. Açıyla uğraşmıyorsun. Tamam mı? Bunu da yapabilirsin. You can take this distance as the distance of the torque equation, R times F. But in that case, you have to find this angle. In that case, mg is not perpendicular to this distance, so you have to take the perpendicular component of mg. But this requires the knowledge of this angle. Or you will prolong this mg direction, and you will take the perpendicular distance to this direction from the elongation of mg, and this distance is already given in the problem. Okay, so that's it. If you think mg times sine of this angle, in fact this is nothing but this component of mg. Well, this component of mg, even if you know, you don't know this distance anyway. So just from observation of the given values, and this, in this case, b is given, so you can choose a proper distance to the point of application with the mg. Okay. The similar thing is true for F3. if you think this distance to F3, there is again a angle which is not equal to 90 degrees. But if you think that the perpendicular distance to the direction of the F3 to the ground, it is given, so you might use this distance times F3 because they are perpendicular to each other, and this may be used as calculating the torque.
We want to find theta. Theta should be the angle more than 90, minus 90, right?
You mean this angle? It is more than 90 degrees, yes.
We want to find theta.
Huh?
Theta will be the angle for the triangle.
This angle. This angle is more than 90 degrees, yes.
We want to apply mg multiply sine theta. We will not put theta.
Are you thinking the torque applied by F3 or mg?
F3.
F3, okay. So we don't have to do anything with mg. So this angle, okay, well, this angle is more than 90 degrees, but we don't know. The problem is we don't know this angle. But you can calculate this angle, okay, if you know the length of the ladder and this distance. But these distances are all not given in the problem.
We can calculate.
You can?
We can find.
How?
We have it's mean 3 with Pythagoras law.
Okay, this is given, right? This is given, but you don't know the length of the ladder, or you don't know this distance. How will you calculate this angle? There is no way to calculate this angle, okay? Okay, we have more examples on this. Okay. If you have further questions, you can ask me on the break. Arkadaşlar, isterseniz dışarı çıkın. Niye şey yapıyorsunuz? Kendinizi burada zorluyorsunuz. There is a way to find the center of mass physically, just by experience. You don't have to think about the weight or the distances. For example, in this example in the board, you might wonder where the center of mass of this system. Just hang this stick that connects these two masses M1 and M2. Find a place on the stick, right, on the rod. When you hang on this point, there will be no rotation. Okay? So once you find this point, that's the center of mass of the system. Or in the horizontal direction, in this direction, this point is the center of mass. If you have a very irregular, geometrical shaped object, and you want to find its center of mass, just find any point on the object. Let's you may choose this point, okay, point A, and hang on it, okay. And when you hang on it over a point, you just draw a vertical line on the object, okay, and hang on this object at any other point you might choose. Any point is acceptable. Let's call this point B. Again, when you hang it, just draw a perpendicular line. The intersection of these two lines is just the center of mass of this object. So this is the way to find experimentally, not by calculating theoretically, the center of mass of objects. If you are curious about an object, and if you want to find experimentally or by trial, then this is the way to do it. So this subject of the applications of torque in dynamical questions is one of the most important subject in this chapter, and also you will have at least 2 problems in the final exam. So be careful in listening this part. So far in chapter 5 and 6, when the applications of Newton's second law, remember we have dealt with the problems like an object is moving down on attached to a string, and a string was over a pulley, and the pulley was not rotating. But this chapter we are going to deal with the rotating pulleys, okay? And we will have these type of questions. We have a mass attached to a string, and the string is wrapped around a pulley, and the pulley is free to rotate without sliding the string, okay? When the string is moving, the pulley is rotating, and there is no sliding between the string and the pulley. So how can we analyze these type of questions? Let's think of this specific example. Okay, so we have a mass m, small mass, attached to a string, and the string is wrapped around this pulley. And when you release the mass, since there will be a tension in the spring, this string, the tension is a force, and it will rotate the pulley around this fixed axis, right? So it's a kind of rotation, and there is a kind of torque in here, because we have a tangential force on the rim of the pulley, and you know the distance to the rotational axis, so you can calculate the torque of T, tension. You have to include this torque and also the rotation of the pulley when you are going to find the linear acceleration of the mass m, okay? So without thinking about the rotation, or without taking the rotation and the rotational angular acceleration, velocity, whatever, all the dynamics related to the rotation of this pulley, you will not be able to find the correct answer for the linear acceleration of m. So the best way to do this, again, show all the forces acting on each object. So you have 2 objects in here in a dynamical motion. One is pulley, it is rotating. It is dynamically not in equilibrium because it's rotating, right? So we have to include this rotation. Also, we have a linear motion of the mass, the small mass, attached to the string. So there are, of course, 2 forces on the string. One is downward gravity, mg, and upward T, tension in the string. This same tension in the string is rotating the pulley around this fixed axis, right? So we have also the rotation. And the rotational angular acceleration of the pulley and the linear acceleration of the mass are related to each other, right? Remember, the linear quantities and the linear quantities, the rotational quantities are related to each other. For example, the linear velocity v is equal to omega, the angular velocity, times the r, radius of rotation. Just like this, the linear acceleration a is equal to the angular acceleration alpha times r. So you have to calculate, you have to first write down the equations of motion for each part, for this one and for this one separately. And in here you will have alpha, the angular acceleration, and in here you will have the linear acceleration. But you know that the linear acceleration and alpha, the angular acceleration, are related to each other. So I will come to this point anyway. But before you start writing down the equations, you have to choose your directions of motion, okay? If you choose the upward direction as positive for the object, the small object mass m, then you have to choose this direction of the rotation as plus, okay? There will be some problems, there will be some special cases that you have to choose the other rotational direction as plus. I will come to these type of questions, but we already know that in the rotational motion, the counterclockwise direction is always chosen as the plus direction. So this is important. So when you write down the Newton's second law for the hanging mass, it is very easy. Let me come to this point. So the first equation is the total forces acting on the object which moves linearly. Okay, this is important. Will be provided by the Newton's second law, and the forces acting on the object which moves linearly, total force, must be equal to its mass times acceleration. This is the Newton's second law. So mg is down, it is negative, and t is up, it is positive. This must be equal to the acceleration times the mass of the hanging object. This is your first equation. The second equation concerns about the rotational motion of the pulley. So Newton's second law for the rotational motion, as you know from previous lecture, just like the Newton's second law for the linear motion, torque is equal to the moment of inertia times alpha. And torque here plays the role of forces, the moment of inertia plays the role of mass, and alpha plays the role of linear acceleration. So what is the torque? When you look at the rotation of this pulley, okay, if you take this counterclockwise direction as the positive direction, the tension will try to rotate the pulley in the clockwise, in the negative direction. So when you write this equation, torque equation, the torque must be taken as negative. This is important, okay? Because we already chosen the counterclockwise direction as positive. But if you observe what the tension force will do on the pulley, it will try to rotate in the negative direction. So the torque then in that case minus, and is minus T times R. Okay, because the force times the distance of this force to the rotational axis, it's just radius itself. This is equal to I times alpha, and I is the moment of inertia of the rotating object, which is, in this case, it is a disk. The pulleys are disk, and the moment of inertia for disks are 1/2 m r square. But let's keep the moment of inertia as I for the time being, and I will put the correct value later. So I times alpha. What is alpha? Or how alpha is related to this linear acceleration? We already know that alpha is equal to A divided by R. Okay? If there is a rotation, then the linear acceleration of the rim on the rotation is related to the angular acceleration as A is equal to R times alpha. A is the linear acceleration of the rim, any point on the rim of the pulley, and R is the radius of the rotation. So we already know that, right? There is no any difficulty on this point. So this, in fact, will save us, because this is the point where these two equations are related to each other. So from this, you can either put, let's say, well, let's choose solve first for t in the second equation, and t in terms of the linear acceleration, the moment of inertia, and the radius. So t is this, and if you put this quantity, okay, from the second equation into the first equation, if you replace t by minus I times A times divided by R square, you will get this equation, okay? Equation 1 and 2 will give you one equation, and in this equation you can easily solve for acceleration A. And from this, you will find A is minus G divided by 1 plus the moment of inertia I of the rotating disk divided by the mass of the hanging object, small m, times R square. Let's put also the moment of inertia of the disk in terms of its mass, capital M R square. Okay, this is not very important. You can always put this and simplify the equation for A in terms of just masses. But one thing you have to be careful in here, A is always a negative quantity, right? Because G is always positive, masses are always positive, and the moment of inertia is always positive. So we have minus sign in it. Why? Initially we have chosen the upward direction as positive, right? But if you release the object, and it will go down. That's why you find the acceleration as minus, because assumption in the first part in the problem before you solving the problem, the assumption was the upward direction as the plus. So if it is A is minus, then that means the object is going down. Yes.
If you want to find the acceleration of bullet, we divide the acceleration over r. You want to find alpha.
If you want to find alpha, what you do is just
A over r.
divide this A by R. That's it. Okay. If you have any questions on solving this problem, well, this type of problems, the most important part is choosing the directions of motion. And which direction will you choose as the plus direction of rotation, or which direction for the linear objects is upward or downward plus. It's up to you. Okay, you might as well chosen the directions as downward as plus, right? And the clockwise rotation as also plus. You might choose this. This is not a unquestionable choice. Okay, clockwise and counterclockwise direction is always plus. You might change this for your specific question. You might choose the counterclockwise direction as negative. Okay, this is up to you. But the direction of the motion of this object and the rotational direction must be consistent. Okay, if you choose upward direction as positive, right, then you have to choose this rotational direction positive for the pulley. Okay, if you choose the upward direction as positive but this direction of motion as negative, then A and alpha will be inconsistent, right? Because the positive A will not give you a positive angular acceleration. So these choices must be consistent with each other. Another example, you have this time an object moving horizontally, okay, and again there's a string attached to it, and this platform is just to provide a frictionless surface for the linear motion of this mass. And this string is going over a pulley, and again pulley is free to rotate without sliding with the tension in the string. And you have, of course, two different tensions, okay, for that string, even that the string is the same, unlike the cases in chapter 5 and 6. Remember, we have taken the tension for the same string all the way down equal to all the way down for the same string we have only one tension. But in this chapter, since the string is rotating a pulley, the different parts of the string will have different tensions. This is very important. And you will appreciate this when I explain the things over this free body diagram. If the pulley is rotating, right, then these tensions T2 and T1 must be different. Imagine they are equal to each other. If T2 and T1 are equal to each other, T2 will try to rotate the pulley in the clockwise direction. T1 will try to rotate the pulley in the counterclockwise direction. But if they are equal to each other, there will be no rotation at all. Okay? So in order to have a rotation, these tensions must be different. Okay, and the problem says T1, the tension in this part in the string, is pulled by a hand, and this is 1.1 newtons. The question is find the tension T2 and the acceleration of the cart in terms of T1. So you will find T2 in terms of T1, and you will find the acceleration of the cart, this moving object on the horizontal direction, in terms of, again, T1. So the right picture is, again, the free body diagram for the objects. And drawing free body diagram is very important, very critical in these type of questions. For the rotating objects, you will draw all the forces that can rotate the object, because you have to calculate the torque, and you will write the torque equation. These are important. And choose again which direction of rotation and which direction of motion of the linear object as plus. If you choose this direction A as plus direction, then you have to choose the counterclockwise direction as plus. These must be consistent with each other. Sorry? This is going in counterclockwise direction, yes. It is counterclockwise, it's plus. But don't worry about is it counterclockwise or clockwise. Choice of plus or minus direction of rotation is up to you. Okay? In these type of questions, you may choose either direction, clockwise or counterclockwise, as plus. It's up to you. But if you choose this direction as plus, then you have to choose this direction of the motion of the linear object as plus. Okay? To be consistent with the rotational direction. So the first thing is to write down the Newton's second law for the linear forces. And for the linear forces on the mass, moving mass, horizontal moving mass, is T2 is acting, is pulling towards left, but I have chosen the left direction as plus, so T2 is plus and m times a. That's it. The second is the torque equation for the rotating object. For the torque has two different torques in here. As I said, one is the torque provided by T2, and the other one is the torque provided by T1. So the net torque is the sum of these. One is trying to rotate in clockwise, the other is counterclockwise. T1R, the small r is the radius of the pulley in here. I think this is not very recognizable for you. Anyway, the radius of the torque is r. Let me show it in here. Okay. So the radius of the pulley is r, small r, and T2 is trying to rotate the pulley in the negative direction, as you see here, because I have chosen this direction as positive, but if you look at T2, it will rotate in the negative direction. So T2 times r will be negative in the torque equation. That's why we have minus T2 times r. We have plus T1 times r. It is the torque by T1. So this will be equal to I times alpha. And alpha is always related to the linear acceleration of the object on the table, a divided by r. And I is 1/2 small m r square. So this is the moment of inertia for the disk, for the pulley, because it is in shape of disk, and disks always have 1/2 mr square. So when you express this in terms of the tensions and the acceleration, you have reached this second equation, and you have the first equation in here. But since T1 is known, and you can replace T2 in the second equation by m times a, this capital M times a, to express a in terms of T1. When you solve these two equations, when you replace T2 ma in the second equation, you will solve for a, and a will be T1 divided by the small mass, the mass of the pulley, divided by 2 plus the mass of the cart. Okay?
So you took downward.
I took for the cart going with respect to you in the left direction as positive. There is no downward force, downward motion. Downward only we have this hand pulling, this tension T1 is pulling down. And T1, of course, will be in the positive direction. T2 is minus, of course, with this direction. So, but here, I care about the magnitude of T2, okay? So T2, well, T2 depends on in which direction, in which point you apply T2, okay? If you look at the point where this T2 is the application force for the mass M, it is plus, okay? But if you think as the torque provided by this T2 on the plate, it's negative because I take minus T2 times R, and it is already shown in the equations. Okay. So T2, if you think T2 as the applied force for the cart, it is positive. Remember, the tension on the strings at different points, there's tensions at opposite directions, you know. So there is two directions for T2. If you think T2 as the applied force on the capital mass, M, the cart, it is positive. But if you think the T2 or the torque provided by T2 on the plate, it is negative. It's a good point it's good that you have asked this point. This is very important. We have two directions for T2 in this problem. Okay.
Hocam, TB'deki küçük M hangisinin kütlesi? Niye onun kaynağı olduğunu anlamadım.
İskan dediğimiz aşağı çeken kuvvet.
Küçük M pulling makaranın kütlesi. Makaranın kütlesi.
Hocam makarayı niye?
Makara bağlı. Makara hiçbir yere gitmiyor. The pulley is not in linear motion, but it's rotating. It is rotating. If it's rotating, the pulley has moment of inertia. Burada evet hiçbir yere gitmiyor. Fakat bir dönme hareketi var. Dönme hareketi makaranın kütlesine bağlı. Eğer çok büyük kütleli makara kullanıyorsanız dönme daha yavaş olacak. O yüzden kütle her zaman devreye giriyor. Sanki makarayı hareket etmediği için, doğrusal bir harekette bulunmadığı için kütlesi nasıl devreye giriyor diye zannedersem aklınıza takıldı. Evet, makara hareket etmiyor, linear olarak, doğrusal olarak hareket etmiyor ama dönüyor. Dönmesi onun dinamik olarak hareket ettiğini gösteriyor. O noktada devreye giriyor kütlesi. So we already expressed T2 and A in terms of T1, and T1 is already given in the problem, so you can calculate numerically as long as you are provided the masses. Let me give a break at this point, but I give a short break, okay, 5 minutes, and then I will continue. Bir çay al gel, tamam mı? Let's continue with this Atwood's machine. It's the elevator problem. If you remember, I don't know, we have dealt with this problem in chapter 6, but at that time the problem was not thinking about the motion of the pulley, and the pulley was fixed. The string was sliding without friction around this pulley, and we have calculated the acceleration for the system. But this time the pulley is rotating without sliding with the string, so we have in fact the motion of three bodies. We have the linear motion of mass m1, linear motion of mass m2, and the rotation of the pulley. So the question is, find the tension and the acceleration of this system, the acceleration of mass 1 or mass 2, whatever, because they will both have the same acceleration. And of course, the acceleration of the pulley, the rotational acceleration of the pulley. Once you find the linear acceleration of the masses, it will be clear because the rotational angular acceleration is again related to the linear acceleration. So find the acceleration of the masses and the tension in the string. So for this, again, you have to fix a direction, first of all. If you choose the downward direction as plus, then you have to be consistent with the rotation of the pulley. In that case, the counterclockwise or this direction of the motion or rotation must be chosen as plus. Okay? And of course, M2 will go up. So, the first thing is to write down the linear Newton's second law, right? And the linear forces. For example, for mass M1, the forces acting on M1, let me also denote the tensions in the string. This will be T1 and this will be T2, right? And this will be M2G for M2 and this will be M1G for M1. So let's write for the first mass, since M1G is down and down is taken as plus, M1G, but T1 is up and up is opposite, so it is minus T1 and this will be equal to M1 times A. Okay. The same for M2. So T2 is so you have to be careful in here. If you choose for M1 down as plus, what is the plus direction for M2? Okay. To be consistent with the motion of M1, okay, we have to choose the direction for the mass M2 upward direction as positive, because if M1 is going down and positive, then M2 must go upward positive. Just like we choose the rotational direction for pulley. Since M1 is going down and it is taken as plus, this direction of rotation must be chosen as plus. Just like this, we do this choice, then T2 minus M2G is equal to M2 times A. Okay? So, yes.
There is two system differences, not the same.
Yeah. Well, two equations. The system is the same.
So if you find T2,
But the thing is here, and just if you think the previous case that there is no rotation of the pulley, in that case T1 and T2 were equal to each other. But in here they're not equal. Okay. So the third equation, as you might guess, will be the torque equation for the pulley. And for the pulley, rotating in the counterclockwise direction is plus. Well, before that, you have to show the direction of forces for the pulley. If T1 is acting up on M1, on the pulley side, T1 must be downward, right? Because this is the rule. On the same string, at different ends, the tensions are in opposite directions. This is the principle. And there is no exception for this sort of principle. And the same for the T2 side. Okay. So with this, now we are ready to write down the torque equation for the pulley. And T1 will rotate in the plus direction. It is obvious, right? So T1 times R. It's the torque by T1. Let me write this to the sideways. T1 times R, and T2 will try to rotate the plane in the other direction, which is minus direction. So I have to take this as minus T2 times R, and this will be equal to the moment of inertia of the plane, I, times alpha. But alpha is related to the linear acceleration A of these two bodies, M1 and M2, by A divided by R. So I have three equations now, and if you are given, if you assume that M1 and M2 and the moment of inertia are given to you, then three unknowns, T1, T2, and A are three unknowns. So you can solve for these three equations then. So how can you attack the problem? If you think here, T1 minus T2 times R, right? This is the torque equation. But in here, you can sum side by side. If you sum these two equations, you will get T2 minus T1 equal to, on the right hand side you have M1, A, M1 plus M2, right? And plus G, if you pass M2 other side, then M2 minus M1. Okay. Well, if you think this equation, then let me erase this. You can express T2 from the third equation minus T1 as minus I times I divided by R times A. So you have T2 minus T1 from the first two equations and T2 minus T1 from the third equation. Then you may equate these expressions on the right hand sides. A, M1 plus M2 plus G, M2 minus M1 is equal to minus I divided by R, A. Right? What? So we have T2 minus T1, this from the two equations, and T2 minus T1, we have R square in here, and here R square. Is that correct?
But I don't understand about the direction. You suppose first here the upward is positive and the other side you suppose downward is positive. But this same picture, same system.
Yes.
How can you suppose this? For the first and second equation, you say M1G minus T1. You suppose T1 is minus and suppose T2 is positive.
Well, for M2, if you choose this as plus, okay, then you will get the same equation, in fact. This equation will be the second equation, M2G minus T2, and it will be equal to minus M2A, because direction for A will be upward, right? And upward with this choice is negative, right?
So
It's the same.
This like angular system.
The only thing is I want to be consistent with the signs. if you choose A, the acceleration for the mass 1 as plus direction for this direction as plus, and the acceleration for M2 it will be in this direction, and the rotation of pull A, the plus rotation of pull A, will be in the counterclockwise direction. I just want to be consistent with all these three, because alpha in here is related to A. They have the same sign, right? They must have the same sign.
Suppose the object like force, right?
Mm-hmm.
Affected of the volume. And you can put instead of mass force downward and force downward. Right?
For mass M2,
You can draw 1 point on the volume. It's mean force downward.
Mhm.
It's F2. It's mean M2 for coming from M2. And you can draw a point, another point, F1. Right?
I don't think I understand you, what you're talking about. You can express maybe on the board. You can show on the board.
No?
Yeah.
Can you put here 1 point on the volume and here 1 point? You can suppose this mass it's like force,
Yes.
and here you have also second force affected
Yes.
on the volume. The
Yes.
first force is direction downward, and here also downward.
Yes. T1 and T2.
So you can say here is angular momentum, right?
There is no angular momentum.
Angular
Rotation.
acceleration, alpha.
Yes. Well, if you have mass in here, the force on the pulley on this side is downward, T1.
And also downward.
And this is also true for that one. So the rotation for pulley happens if the pulley rotates in this direction. That means T1 is larger than T2.
Yes.
Okay? And the acceleration for the mass 1 is down, and for this one it's up. But I can choose different coordinate system for each mass. This is up to you. You are free. But if you want to be consistent with the rotation and the direction of motion of this one also, so you have to be careful in here. If T2 is going up, M2 is going up, I can choose as well this direction as plus. In that case, the acceleration for this one will be plus. And the acceleration for this one again is plus. And the acceleration for the pulley again plus. All the signs must be consistent. Okay?
Also, we can find just alpha. After that, we can divide alpha over r
Yes.
to find acceleration.
Yes.
Right?
Alpha and A are just related to each other by just a constant.
So
But the directions must be the same. Right?
yes.
If the pulley is rotating in the counterclockwise direction, then M1, A must be in the downward direction, and for M2, in the upward direction. Okay, so for this, then I get A in terms of, well, A here in this right-hand side also. Let's take all the A's on the left-hand side, and I have A M1 plus M2 plus the moment of inertia of the pulley divided by r square on the left hand side, and on the right hand side I have M1 G times M1 minus M2, right? So let me carry over this on the second page. Then A is equal to G times M1 minus M2 divided by M1 plus M2 plus the moment of inertia of the pulley divided by r square. So your result also must be consistent with your choices of direction. So look at this equation. A is positive as long as M1 is larger than M2, right? Because I already assumed that M1 is larger than M2 because M1 is going down and it's plus. So it's true. In that case, if M1 is larger than M2, A will always be positive. And this is very consistent with my choice of directions, okay? So, well, A will be in terms of G. If you had no rotation of pulley, then Edwards machine in chapter 5 or 6, the acceleration, if you check your previous notes, lecture notes, the acceleration is equal to M1 minus M2 divided by M1 plus M2 times G, if there is no rotation of the pulley, okay? And there is no friction in the pulley. But when you have a rotation for the pulley, this moment of inertia of the pulley will resist motion, will resist the acceleration. If you have larger rotational, larger mass for the pulley, then the acceleration will be less because larger mass will increase the moment of inertia, right? Well, not only the mass of the pulley will increase its moment of inertia, also if you use with the same mass a larger radius, okay, because the objects which has larger radiuses are more difficult to rotate, right? Because they are huge. Right. So this all information can be interpreted from this acceleration equation. Okay. Once you know, but if you have, well, you might find this acceleration anyway, but in some way, if these plus signs, one of them is minus, then you are certainly doing something wrong. Okay? Just check yourself at the end. You must always have all the quantities in the denominator, in the acceleration expression, always positive. These signs must always be positive. If you have somehow negative signs in here, you are doing something wrong. Okay? Definitely, 100%. When you are solving the problems, just keep this in mind. But once you find A, you can easily, I am leaving it to you, express T1 and T2 in terms of mass M1, M2, and acceleration and the moment of inertia of the disk. So I'm leaving to find T1 and T2 in terms of M1, M2, and I. Well, I know it is somehow difficult to understand for the first time, but if you look at the examples on your textbook and also in the web page, Google, you have millions of examples on rotating objects taking these signs. There are many examples, solved examples, so you can understand this well. Yes.
Kamas'ta ilk 6 bölümün pratikleri var da diğerleri açacak mısın? Siz mi açacaksınız?
Açacağım. Bu hafta açıyorum. Next question. Do you have a spool? Do you know what the spool is? Makara. I don't know the Arabic word. Makara is the same. Yes. We use this in sewing, right? In sewing the things. So the spool has the inner radius, since you know it. This inner radius, its string is going over the inner radius, and also we have the outer radius of the spool, right? When you just pull the string, when you put the spool on the ground and spool the string, in which direction the spool is going? If there is no sliding of the spool is, assume that it's not sliding, it's rotating. When it's going, it's rotating, not sliding. If you pull the spool in this direction, the string, which direction that the spool will go?
First, go
With constant T.
Yeah, first things.
Uh-huh.
First time it will go for positive leg. Ben bir tepki uygulanır öleceğim. Ondan sonra kayma zaten varsa sürtünmezse o yüzden dolayı.
Okay.
Geriye bırakmaya gider.
How many forces acting on the spool? Okay, yes. 3. That's true. First force is the applied force T, right? It is pulling. Well, if the spool is rotating without sliding, there must be a frictional force between the spool and the ground, right? And in which direction is this
Right. Friction. Left.
friction?
Left.
The opposite.
Well, your right and my right is not the same. Is it in this direction or in this direction? This
Friction, right?
Left hand. Friction.
the opposite to the T.
The opposite.
Why? Okay. When you ask why, you have to give a physical answer to that. I am pulling T. You say the friction is in the opposite direction. If there were no friction, the spool will rotate without going in linear direction, right?
Hareketsiz, not moving.
So if you pull it, then the spool will rotate in counterclockwise direction, right? But since it's not rotating in the counterclockwise direction, something is preventing its rotation in the counterclockwise direction. That something that prevents its rotation in the counterclockwise direction must provide a rotation in the clockwise direction. So then, this is this is possible only when you have a force on that rim in this direction. That explanation is the physical explanation. So you have to have the frictional force in this direction.
You can say Newton third law. Newton third.
Well, Newton's third law, it's action-reaction. It is not the case in here. Okay. Well, the third force is, as you might guess, is downward gravity. But this normal force, downward gravity, has no effect of the motion of the spool in the horizontal direction. We only concern the horizontal direction. So the question is, I will find the linear acceleration of the spool, A, in terms of the applied force T and the mass of the pulley. Okay, so what to do? How can I...
So what is the third force?
Well, third force is mg down and the normal force and up at the contact point of spool to the ground. But since the motion takes place in the horizontal direction, just it is enough to think the forces T and F only. I have to start with the total force, right, is equal to M times A. So, and also, there is torque, right? Because the spool is rotating, and this rotation, is it in uniform speed or in an increasing speed? If the pulley is linearly going in the right direction with some acceleration, which is non-zero, what can you tell about its rotational acceleration? It has also a rotational acceleration. It must have a rotational acceleration. If it has a linear acceleration and it's not slipping on the surface, it's rolling and going, then there must it must have a rotational acceleration. That means you have to also write down the torque equation, two equations, the moment of inertia times alpha. But we know A and alpha are related to each other again, right? And A is equal to alpha times R, or alpha is equal to A divided by R. Anyway, So let's write down the first equation first. Then, if you choose this direction as plus, then T is in plus direction, minus, because F is in the opposite direction, the frictional force, right? And this will be equal to the mass of the spool times A. The second equation. Well, the second equation concerns the rotation of spool. If the spool is going in the right direction, which direction it will rotate? It will rotate in the clockwise direction, right? In this direction. And I have to choose this direction as plus. Remember, I said in the rotational kinematics, the previous chapters, we usually take, well, was the convention, the counterclockwise, the clockwise rotation is usually taken as minus. But this is not a universal rule. If you choose in this problem A as positive to the right, then you have to choose the rotational direction as, the clockwise rotational direction as plus. Because A and alpha are in the same direction, right? If A is to the right, then alpha must be, it is rotating the pulley, the spool in clockwise direction. I have to take this as plus, because A is plus.
You suppose it's rotating on the clockwise direction, but if you put rotating counterclockwise.
If the spool is not sliding, and if it is going in the right direction, it must rotate in the clockwise direction. There is no way, no other way. Okay. Anyway, let's write down the torque equation then. So with this choice of plus direction of rotation, what is the torque provided by F? The inner radius is small r, the outer radius is plus capital R, you see here. If you want to write down the torque provided by the frictional force F, is it plus or minus? I am taking this direction as plus. It is plus because F will rotate the spool in the clockwise direction, and I take clockwise direction as positive. What about T? T will try to rotate in the counterclockwise direction. Then the net torque is Fr minus T times small r, because the distance to the rotational axis for T is small r. It has inner radius, and this is equal to the moment of inertia of the spool times alpha. And in alpha, instead of alpha, I put A divided by small r or capital R? A divided by small r or capital R? Capital. Because it's rotating on the outer radius. So I have two equations with two unknowns. And you might express in the first equation F, the friction, in terms of T and M times A. So T minus M times A times capital R minus TR equal to I A divided by R. I want to express A, this is A. I want to express A in terms of T and mass M, and also a moment of inertia. But moment of inertia is always can be written in terms of the mass M, because it's a disk 1/2 capital M times the big R square, because it's rotating over the big R. So A we have m times a air minus on the left hand side. A, we have I divided by r plus m times r, and on this side I have t r, the capital R, minus small r. So, oops, then A is equal to T times R minus R divided by the moment of inertia divided by R plus m times R. Okay, so you can further simplify this when you put I is equal to mr square and multiply both numerator and denominator by R, you will get a better expression for A. So this is the linear acceleration in terms of T, applied force, and the mass, and also of course radiuses. You see, A is always positive because R, the capital R, is always larger than smaller, right? Because it's pull. Any questions on this? Yes.
So when you pull the, when you're rolling the
Spool.
yeah, you say it's rotating on the clockwise.
Yes.
But how is it? You're pulling and like this. It's not clockwise.
I'm pulling, and it will go in this direction. It will rotate in the clockwise direction.
Why?
It is clockwise direction.
Why?
Why?
Böyle çekiyoruz geri gitmez mi?
You want and come like this, not like this.
The spool, if you pull a horizontal force like this, the spool will go in this direction.
Rotating.
If the spool is not sliding over the surface, if it is rotating, okay? If the surface is not frictionless, if the surface is frictionless, then this is something else.
So here the
But if the point where the spool is in contact with the ground is not sliding, then always the spool will go in this direction and it will rotate in the clockwise direction. I will show it to you, okay? Because you are fifth, there is lab in this, and I will bring the lab, you to the lab on the way. And we have a spool like this huge. I already tested it, okay? So you will satisfy about the result. If you want, I can show it to you today.
Hocam kaysaydı
But there is more interesting thing coming. If it's sliding, then it's something else.
öyle yapsak.
Maybe it becomes same center then.
If it's sliding, okay, without any frictional force, then what happens?
It's rotating around itself. Then to the
There will be only one force, T, right? There will be no any frictional force, right?
Hocam sonuç ne şimdi, siz neyi söylüyorsunuz, ben tam olarak anlamadım. Çektiğiniz zaman bu tarafa mı geliyor?
Çektiğin zaman çektiğin tarafa gelir. Yuvarlanarak.
Sürtünme varsa ya da...
Sürtünme varsa, kaymıyorsa yüzeyde.
Tamam, bu normal bir şey.
Sana normal mi geliyor? Onlara normal gelmiyor.
Yok hani mantıklı olarak sürtünmüyorsa zaten gelir. Hani,
Sürtünme var.
hani sürtünme varsa pardon. Sürtündüğü için. Sürtünmüyorsa zaten o
Okay.
kayar falan yapıyor.
I like your confusing up very. Then I want to confuse you more. Think about this.
Can we do it on Thursday maybe?
We can do it online now, right now. Okay. You have. We'll go. Okay. Let's solve this problem.
What will happen when the surface is
Frictionless.
friction and also it's sliding?
If it's not friction, if it's frictionless, there is no friction. Sliding. Okay. this is something else, but I have to, I will answer this, but later, okay? Because I have to finish this. So think about this. Which way it will rotate? Go.
Hocam bir şey soracağım. Mesela bu halka olarak düşünelim. Bunun etrafında o T dediğimiz şey sarılmış bir şey mi?
Tabii makara. Makara biliyorsun ya makara.
Yani sarılmış bir şey.
Tabii makarayı biliyorsun. İçerideki ipin sarıldığı bölgenin yarıçapı dış yarıçaptan daha şey.
Burada çekersek hem bu yönde olduğu için bu şekilde dönerek ilerleyecek. Sürtünme olduğunu.
Okay, so think about this. Again, we have a friction. We have friction. Okay, the spool. There is only one way to move the spool on the surface. It will roll without sliding. It will roll without sliding. There is friction. Okay, so the same. In the first case, okay, there is friction. There is always friction. The spool is going, rotating without sliding.
But with friction.
With friction. But this friction is not kinetic friction. It is static friction. I explained this before. If there is a wheel rotating and going, then the point that the wheel touches the ground, it has always zero velocity. Okay? If there is no sliding, the point it touches the zero velocity. Then that means momentarily the point of the wheel is always not in motion. Okay. Although the wheel is going, but the point that the wheel is in contact with the ground is not going anywhere. So the type of friction in here is static friction, although the wheel is in kinetic motion. I think you have to think about this maybe carefully, but well, this is it. Okay. What is the direction of friction in that case?
Friction is opposite.
Opposite again? Like this? Like this? Or? I'm having fun with you.
So is it rotating?
But again, it's not sliding, it's rotating and there is friction. It's rolling without sliding. So, think to this type of these type of questions. If you want to determine the direction of frictional force, static frictional force, you will think the opposite way. Suppose there is no friction. In which way the spool will rotate when you pull it? It will rotate in the clockwise direction, but in the previous case, it was rotating in the counterclockwise, right? In the other way. But in here, if there is no friction, it will rotate in this direction. Okay. But if it is rotating in this direction, okay, to prevent this rotation, which direction of the friction must be on the wheel? It must be in this direction, right?
Yes. Down.
It must be in this direction because the spool is going to the right without sliding, and this sliding is prevented only if you have the friction in this direction.
So you suppose the point which touch the floor.
Yes. Yes. The frictional force is in this direction. Okay. So, you might think that you will have maybe the same acceleration with this one. Let me carry this acceleration over here. Okay? The previous acceleration. The previous acceleration in terms of if you take I 1/2 mr square, then
Hocam clockwise mı anti-clockwise mı?
Hocam arkadaş diyor ki şu alttan iple çekersek nasıl diyeyim sağ tarafa doğru döner diyor.
Sürtünme o tarafı. Peki o olduğu için bakın. Onu durduracağız ona. Durdurduğu için.
So is it made up of rubber? Maybe I tried to I
Okay, this is the acceleration in the first case, okay? But now let's calculate the acceleration in here, the second case. So, if you want to write down the Newton's second law, then the total force, this direction as plus, okay? If you take this direction as plus, then the direction, since it's rolling in the direction of t, and it's rolling in the clockwise direction, and I will take also the clockwise direction as plus. Okay? So, t, this time plus F, must be equal to mass times A. Right? Because both forces are in the same direction. What about torque? The total torque is equal to I alpha. So, first of all, think the torque provided by T, okay? So, T times, so since T is rotating the spool in the plus direction, so it's plus T times R, smaller. But F is trying to rotate in the other direction, so it's minus F times capital R. This is equal to I, A divided by R. Okay? So from this, you will see that if you work everything out, then in that case, the acceleration will be equal to 2 divided by 3 Tm. This time R plus the capital R plus small r divided by R. In previous case, the acceleration was up to this point the same, 2 divided by 3 T over M, R minus small r divided by R. But in this case, we have R plus R. So we have a larger acceleration. If you pull the spool from top, it will have, with the same force, T, it will have more acceleration, larger acceleration, than this case. Okay? In this case, it will go with a less acceleration. So you pull. Well, this is relatively easy, right? Again, we think only the case the spool is moving without sliding. It moving, rolling, okay? There is friction. There is friction. So in which direction it will go? Left. This is very obvious. Because, why? Which force is going moving the spool to the left? Which force? T? No, T is going up.
Friction force.
friction force.
Frictional force. Then the frictional force must be to left. How? Good question. If you think the ground has no friction, frictionless surface, okay? When you pull the string up, in which direction it will rotate? It will rotate this direction, right? But we want to prevent this rotation, right? And the friction must be in this direction. The only force that prevents this rotation, there must be a force in this direction so that it will prevent sliding. So this is the way to determine the direction of friction, and the friction force in this direction. When you pull the spool up, the spool will go left, and the force that pulls or that moves the spool to the left is the friction only. There is no tension. T contributed to this motion. Okay. What time is it? I want to finish here. If anybody